Welcome to Physics Made Easy channel. Now we shall be doing the last topic of this chapter, the very first chapter of electronics, that is semiconductor physics, in which we have studied conductor insulators and basics of semiconductors, particularly intrinsic semiconductors, extrinsic semiconductors, NNP type, and then difference between them, doping. These were the basic topics, and one other important topics, band theory. Now let me clearly state that the topic of band theory is important from theory point of view, and the topic of N and P type semiconductors, extrinsic, intrinsic semiconductors, and on which these topics they are important from numerical as well as from MCQ point of view. One of the theory question has been asked on this very formula in NEET. This very formula, equation number 2 and 3, a theory question has been asked. With rise of temperature, band gap changes in silicon or germanium. The question was on this topic, and when we shall do MCQs, I will cover this at that time. And now the basic approach. Listen once again. I will summarize this sum from shortcut point of view. After completion of this chapter, and for at present I will strongly recommend that kindly recommend these two relationships and other important formulas. For example, in extrinsic semiconductors, the the number density of electrons or hole is not equal. What does he mean to say? Ne number of electrons is not equal to number of holes in case of extrinsic semiconductors. In case of intrinsic, they are equal. And NH, number of density of holes, Ni square, number density of intrinsic carriers, that is electrons or hole, in pure semiconductor. In N-type semiconductors, number of electrons is equal to number of donors. As electrons are majority charge carriers, so Ne and Nd, they are much higher than number of holes NH. In P-type semiconductor, the number density of electron NH is equal to Na. This is much more greater than Ne number of electrons. Holes are in MCC. Our MCC means majority charge carriers. So now majority charge carriers, if I draw a table, always wherever possible, tabulation is easy to remember. Now this is one type. For example, I have got N-type semiconductors, I have got P-type semiconductors, and here majority carriers, majority current carriers, majority current carriers. In this it is electron, in P type it is holes, and minority charge carriers, minority current carriers, in N it is holes, in P it is electrons. So draw this table with your own hands with the clear handwriting. So I will revise it. In N type, majority charge carriers are electron. In P type, it is the holes. And in minority charge carrier in N type is holes, and in P type it is electron. And the next is this relationship. Number density of intrinsic current carriers of a semiconductor varies with temperature. Now these are the intrinsic current carriers. In this we take only intrinsic current carriers and not the current carriers due to doping. Intrinsic current carriers, they simply follow the Maxwell law of distribution, statistical distribution, and this is Eg is band gap energy divided by 2 kT. KT is the measure of energy at room temperature. N naught, number density at 0 Kelvin. K Boltzmann constant, T absolute temperature. For a given Eg, As the temperature T increases, Ne increases. Distinction between intrinsic and extrinsic semiconductors. It's a pure semiconducting material and no impurity atoms are added. It is impure. Impurity is added here. And here impurity atoms are added. Examples are crystalline, pure silicon. Examples are germanium crystal, P-type and N-type. You can say if they are, if pentavalent impurity is added, then it is this. If trivalent is added, then you get P-type. If pentavalent impurity is added, then you get N-type. Number of free electrons in conduction band and the number of holes. Note down. Free electrons are always in conduction band and holes are always in the valence band. Number of holes in the valence band and number of electrons in the conduction band, they are equal. That is Ne is equal to NH. Now in this case, in extrinsic type, they are never equal. And here I would like to say Ne is larger than NH, in which case N-type. And in P-type, it is P-type. It is now its electrical conductivity is low. And here electrical conductivity is high. Its electrical conductivity is a function of temperature alone. It depends upon temperature as well as quantity of doping. The doping, quantity of doping and temperature in case of extrinsic semiconductors, and in case of intrinsic it is temperature only. And then difference between N and P type. This is also very much important. So in this case, group 5 pentavalent impurity. N type, it is pentavalent impurity, arsenic, antimony, etc. And P type, in P type it is group 3 impurities which are used. And next, impurity atoms added to provide free electrons in N type. In this case, they are provided to holes and they are called acceptors in P type. This is P type. In P type, acceptors, and here we call them donors. Donors. The donor impurity level lies just below conduction band. Donor impurity level just below conduction band, and this acceptor just above valence band. We have the diagrams. This is acceptor level just above valence band, and here donor level near just below conduction band. And now the electrons are majority charge carrier. Percentage of holes are in minority. We have already stated that in this case number of electrons are larger than number of holes. In this case number of holes are larger than number of electrons. The free electron density is much greater than hole density. This is what I have written. And this is the case of N-type. And this is the case of P-type. This is the case of P-type semiconductors. And now we will take up the issue of electrical conductivity. We are going to consider a cylindrical block whose length is L, area of cross section is A, Ne is the electron density and NH is the hole density. V will be the potential. Now this is this Ne Ne, number density of electrons. This is number density of electrons, number density of electrons, number density of holes. This is drift velocity VH, drift velocity of holes. This is drift velocity of electrons, IE, electronic current. Note that this is IE is electronic current and this IH is hole current. And now this is basically drift current, and the value of IE is NeVd. Note it down. Ne, n number of electrons, E into drift velocity of electrons, and here I am adding E in the feet. And on the same level for holes, this is A NH electron and V holes. Now we will add both of them. We will add them up and we will get I is equal to IE plus IH. And this is A and E. Here we have got NeVe plus NH into VH. Now current density J is I by A. We know it very well. And this is equal to E into NE and then VE plus NH and then VH. So this is the formula for current density. And this is the formula for intrinsic semiconductor. And now we can change it. Basically what I got is J. J is equal to sigma E. You can also get J. J is equal to sigma E. Sigma is electrical conductivity and this is 1 by rho. You can also write J is E by rho. So what I can write is E by rho is equal to current density and this is small e NeVe plus NHVH. This is what do we get. And now 1 by rho we will divide by E. We will divide by E. E will be kept common and inside I shall be having NeVe divided by E plus NHVH divided by E. This is what do we get. And this is mobility sigma. Sigma is equal to E then Ne mu E plus NH mu H. This is sigma. Sigma is basically electrical conductivity. Sigma. This is basic formula. Now we will modify it for different types of conductors. So this is the formula for sigma. And this formula is well written here. Now to avoid confusion, I will change the color. This is the formula. This is the formula which I have proved. Now, quite sure, in intrinsic semiconductor, all of them are equal now. We are taking the case of intrinsic semiconductor, all of them are equal. Ne is equal to Nh. Now, what I will write, sigma is equal to E Ni plus sum of mobility of electron and hole. This is charge E. Next, current density in a semiconductor. So this is the formula that we got, sigma. From sigma even you can have the formula for J also. Multiply both sides by E. We know that VE is equal to mu E into capital E. VH is equal to mu H into capital E. Both of them are equal. Now if we multiply both sides by say E, then sigma E will be equal to E Ni mu E into E electric field. I will directly write VE, and similarly here mu H into E. Mu H into E is VH. So I have replaced this. And this is basically J. From here we get J is equal to sigma E is equal to E Ni VE plus VH. Now, this formula for N-type semiconductors, so this is the formula here. Now, in case of N-type semiconductor, one is you can drop NH, another is Ne is equal to this. The formula for J in this case is E here NeVe. This is the general formula VH. Now this we can reject because VH is much less than this, NH is much less than this. So this comes out to be E Ne into VE. Now Ne is equal to Nd. So this is equal to E into number of donors multiplied by number of electrons. So J is equal to number of donors multiplied by number of electrons multiplied by drift velocity of electrons. So this is the formula of current density for what kind of conductors? N-type. For P-type, in P-type, semiconductors, we are taking the case of P-type. Note down this and this as well. It means sigma will be equal to E into number of acceptors into velocity of hole, drift velocity of hole. So this is basically the formula of for P-type. This is basically the formula for P-type. And now the next formula that we want to do is conductivity of intrinsic semiconductors. This we have already done, that this is equal in this question. It has appeared in NEET examination. Question on this. question on this formula, even in your other examinations, questions on this formula, it appears. Questions on this formula, Ni. Ni is the number density of intrinsic carriers. The conductivity of intrinsic semiconductors sigma I is equal to E into Ni mu E, Ni mu H. And this is the basic formula. Variation of mobility with temperature. This is very important formula. Mobility of charge carriers vary with t raised to power minus m. Now this minus m, it means this is basically inversely proportional to temperature. As temperature increases, mobility decreases. For germanium, now how this question was asked? For germanium, it decreases more quickly. For electron, now change in mobility for, I would like to say, mu hole. Change in mu hole is larger than change in mu electron. And now this is the same formula. For holes, the formula is this. For electrons, the formula is this. It means temperature. If I write it more clearly, I will make comparison of mu E only. Mu is inversely proportional to T raised to 1.66 for germanium, and mu E is inversely proportional to T raised to power 2.5 in denominator. So it sharply decreases for silicon. The rate of decrease of mobility with the temperature for silicon is larger than that for this electron or for germanium. And now below 200 Kelvin, the charge energies are only sufficient to partially ionize the atoms, and number of mobile, I will directly analyze the graph. Now here at very low temperature 100 Kelvin, donors, they are not ionized. At this temperature, donors are partially ionized. As we increase the temperature, more and more donor gets ionized, and the number of charge carriers increases and current may increase. And here, all the donor atoms have been ionized. And if we still go on increasing the temperature, then at this place, now, this will stop acting as an extrinsic semiconductor because all the donors have been ionized now. Now from onwards, this will behave as intrinsic semiconductor. Now, if you want to change extrinsic semiconductor to intrinsic, now one important question, if you want to change from extrinsic semiconductor to intrinsic one, what you need to do from here, what you need to do here, just one thing, raise temperature, or for T more than 400, extrinsic semiconductors, they start acting as intrinsic one. Lodge. This is the very important point. The density of thermally generated pairs begin to increase exponentially. And at this temperature, electron and hole density approach equality, the conduction process becomes intrinsic. Note down this fact. This is very important fact. Operating range. It means operating range is 80 to 100 degrees Celsius, and for germanium, and for silicon it is this. This is for silicon. This is for silicon operating range, and this operating range is for germanium. And with this, I have finished with this chapter. And in a revisionary lecture, I will just point out the important points. We will revise the whole chapter in 10 to 20 minutes. 20 minutes in my next lecture, there will be revision. And then, with these words, I finish this lecture and request you to share it if you like and comment if you don't like.